Alright, let's think about assigning the relationship between these two molecules. And as we've discussed, the first thing to do is to make sure that they have the same formula. And if we count carbons across, we'll count 4, 5, 6, 7, 8. I get 8 carbons across in the left molecule, and 7 carbons across in the right molecule. And so at first it might look like they are completely different. One has 8 carbons, one has 7. But if we look at the substituent here, there's a methyl group on the left and an ethyl group on the right, and that brings them both to the same number of carbons. They both have 9, and then they have an OH and a chlorine. And so I would say that they do have the same formula. So they are not different molecules. Do they have the same connectivity? Well, the OH is on carbon 3 in both cases, and the Cl is on carbon 4 if we count from the left. And then we have this carbon 6, which has a branch point, but it looks like carbon 6 has some differences. However, if we consider on the right side that the longest chain simply goes up instead of continues to the right, then I think you'll agree that both have a methyl group on carbon 6. So it looks like they have the same connectivity as well. So they are not constitutional isomers. So the next step is to look at the stereocenters. And if we look at the OH stereocenter in each of them, it appears that it is inverted. And of course, it's good practice to be able to assign the configuration here. So if we do that, the OH gets priority 1, the carbon bearing the chlorine gets priority 2, the ethyl priority 3, and the hidden hydrogen that's not there is priority 4. And then if I count 1, 2, 3, I get S, and over here I flipped it, so I get R. I'll leave it to you to prove that it's R. But since we've inverted the OH from a wedge to a dash, I think we can assume that it is R. If we look at the chlorine, it is also a stereocenter. It has priority 1 on the Cl, priority 2 on the carbon bearing the OH, priority 3 on the right side of the molecule, and the hydrogen is pointed away from us, and so we can count this way, and that gives us, again, S for this chlorine, and over here, I think we can safely assume that it is R for that chlorine, as it is also inverted. Now, you can see the inversion of the OH or the chlorine substituents very easily the way I have these drawn. However, at carbon 6, it is not necessarily obvious if it's inverted or not, and so it's probably best to assign that configuration using the Kohn-Ingold-Prelog priority. And so let's see if I can switch to green here again. The highest priority should be the left side of the molecule. Second priority is the ethyl, third is the methyl, and then of course if we draw in this H, that is the fourth priority. And so the arrow goes counterclockwise, but you see that the H is in the front position, not the back position. So we need to assign counterclockwise should be clockwise, so this is the R configuration at carbon 6. If we do the same thing at carbon 6 on the right molecule, the priorities should not have changed, but perhaps their relative orientation has changed. So 1 for the rest of the molecule, 2 for the ethyl, 3 for the methyl, and we number them 1, 2, 3. That goes in a clockwise direction. The hydrogen is in the correct spot for correct identification, so this is also R. Okay, so we have R and R on carbon 6, but we have S and R on carbon 3, and we have, where is that, S and R on carbon 4. So you've probably already determined that these are diastereomers. Now our analysis, of course, has taken a few minutes. With practice, you'll get a lot quicker at that, but I just wanted to give you a complete analysis here. And so it's very quick to observe that carbon 3 and 4 have been inverted. And so that should bring your attention to carbon 6, where you can observe the need to assign priority and thus absolutely determine whether or not that carbon also has been inverted. And so we have some carbons, some stereocenters are the same, and some are inverted in this case, and that of course leads to the diastereomers. Okay, let's look at one more example. And here we have what looks like some relatively simple molecules. This one looks like it doesn't have a stereocenter. I'm going to put the chlorine right there. And so we have this single stereocenter drawn on our page in what looks like, we'd use this drawing technique to show a tetrahedral carbon or even methane in its tetrahedral geometry. And so we can observe that there is an H, a Cl, and a methyl along with the ethyl on both of these carbons, so they have the same formula, they have the same connectivity because they're relatively simple molecules. The only question is has the stereocenter been inverted? And there's a couple different ways we can establish this. I'll look at a few of them with you. The first one is to observe that there is free rotation around this CC bond. The bond from the stereocenter to the ethyl can be rotated. And if we rotate that a third of a rotation, right, the chlorine will be pushed down. The carbon with the methyl will be pushed over to the left in the plane of the page, and the hydrogen will be pushed up, also in the plane of the page. And that's what we get over here. So by rotating around this CC bond, this dashed bond that I have hidden back there with the ethyl on it, I can achieve this this setup. And so with that observation, we can label these identical. It's simply a CC bond rotation that allows us to go between these two drawings. And that does not involve the breaking of bonds or the rearrangement of bonds or atoms. It's simply a bond rotation, which happens, we know, all the time at room temperature. So these are identical molecules. Another way to see this is to assign Rns configuration. Most of the time, I hope you're catching on, one of the possible ways of solving these problems is to always assign R and S. And so let's think about that. And we'll notice here that the hydrogen, in this case, is in the plane of the page, as is this hydrogen. So we either need to redraw these or envision them like a Newman projection. We can envision them like a Newman projection looking down that bond. So we're looking at the dotted carbon. The hydrogen is going back. The chlorine will be up, and then the methyl and the ethyl. And then we can draw the hydrogen if we want, but technically we're looking down the CH bond. But this, you can see how this Newman projection, or this sort of pseudo-Newman projection, helps us put the hydrogen in the back, which is where we want it. And so now we can assign priority. Chlorine is obviously highest priority. Ethyl is second. Methyl is third. This gives us S. I'm sorry, this does not give us S. This gives us R. Right, clockwise direction. Okay, so the first one is R. So now we want to establish whether the second one is R or is it different. In this case, we need to do our pseudo-Newman projection as though we were looking straight up at the molecule from a downward orientation. And again, this, let's say that the chlorine is again sort of up, the ethyl, and then we're looking along the CH bond, and so that automatically puts the hydrogen in the correct spot. And you can already see that this orientation is the same as the one I had before, so there's really no need to establish or assign priority. We're going to get R as well right here, and so of course they are identical. There's only one stereocenter. It has not been inverted. They are both R, so these are identical molecules.